Now that we have established the sum and difference identities for both, for sine, cosine, and tangent, I guess there's three of them, we're going to use those identities to develop more identities, basically. We'll just keep building trig identities here. The next one we're going to look at called the double angle identities. And I have a few identities written up here, the sum identities for the cosine, sine, and tangent. And we're going to use those specific identities to come up with double angle identities. Basically, a double angle identity is an expression that would represent, we'll start with cosine, the cosine of twice an angle, right? Cosine of 2a rather than the cosine of a. So if you knew values for the cosine of a, can you determine the values for the cosine of 2a, double the angle? And it turns out you can. So the trick to this is noticing that 2 times anything is that thing plus itself, right? 2a is really a plus a. And so we can rewrite this as the cosine of a plus a. Now we have a formula for the sum, cosine of a sum. We have a plus b in the formula, but the a and the b could be the same thing, a and a. And so what we're going to do is replace all the a's with a and all the b's with a in the formula, okay? Basically plugging a and a in for a and b. Not too bad. To do that, we end up with the cosine of a times the cosine of a, right? This b becomes an a, minus the sine of a sine of a. All right, simple enough. Now, when I look at each of these two terms, they have a repeated factor, right? Cosine a times cosine a. Anything times itself is that thing squared. So this is really equal to the cosine squared of a, right? Cosine squared, cosine times cosine. And here we have sine a times sine a, which is the same as sine squared, right? So this is minus sine squared a, right? This is going to be the simplest form that we can put it in, and it's going to be a new formula that is equivalent to the cosine of 2a. So we're going to have a double angle identity. I'll set it off to the side here. That basically says the cosine of 2a is equal to the cosine squared of a minus the sine squared of a, all right? And so now anytime you see the cosine of 2a show up in a proof or in an evaluation of a trig identity or a trig value, we can always replace it with cosine squared of a minus sine squared of a. And so if we know the cosine squared and the sine squared, we can use this formula to calculate the cosine of 2a, right? We can actually construct a couple of other formulas for this because we also know the Pythagorean identity. Notice that we've got cosine squared and sine squared in here. We also have seen when we studied fundamental identities that the sine squared of theta plus the cosine squared of theta is equal to 1. And so I could solve this equation, this Pythagorean identity, for either the sine squared or the cosine squared and substitute it into this formula. So let me go ahead and do that real quick. Let's say I solve for the sine squared. That means I would subtract the cosine squared from both sides. You'd have 1 minus the cosine squared of theta. Well, if I were to, or theta, or a, whatever the angle is, it doesn't matter the variable there. And so if I take 1 minus cosine squared and plug it in for the sine squared here, we would end up with the cosine, and I'll write this off. We'll develop it on the left and then I'll put the final formula on the right. Cosine of 2a equals the cosine squared of a minus the sine squared gets replaced with this expression. Of course, I'll switch it over to a's. So it's 1 minus cosine squared of a, okay, using the Pythagorean identity. Now I distribute this minus sign and then combine my cosine squares. So I get cosine squared a minus 1 plus cosine squared a. And anytime you add something to itself, you get 2 of them. So it's 2 cosine squared a. So we'd call this 2 cosine squared a minus 1. Okay. This gives us a formula to relate the cosine of 2a to only the cosine of a. Right? So if we didn't know the sine, if we only knew the cosine, we could utilize this new formula. All right? So we'll put that up here as an additional formula for cosine of 2a. It is 2 cosine squared a minus 1. Right? Okay, so a second formula. Now we're going to create a third formula. I said that you didn't have to just solve for sine squared. We could have solved for cosine squared and done the substitution. So we'll do that instead. Erase what I did here. And we'll make that adjustment. So here I'm going to solve for cosine squared by subtracting the sine squared. So we'd have cosine squared a, or theta, equals 1 minus sine squared theta. Okay. Now we're going to replace the cosine squared in the original formula with 1 minus sine squared. And so I would have the cosine of 2a equals, instead of cosine squared, I would have 1 minus sine squared. And we'll replace the theta with an a. And then minus the sine squared. All right, so this is essentially cosine squared minus sine squared still. Again, I would simplify this. I have 1 minus sine squared. Subtract it twice, it's like subtracting 2 sine squares, so I would simplify this by combining like terms, and I'd get 1 minus 2 sine squared a. Right? This is another formula that we can use where we only need to know the sine of a to be able to calculate the cosine of 2a. Right? So we'll put this one off to the side. So cosine of 2a is also equal to 1 minus 2 sine squared a. These 3 formulas are interchangeable. They can each be used in any situation, but there are certain situations where one might be more useful than the other, okay? Or may simplify an expression in a better way than the other ones might. Okay, so that gives us 3 expressions for the cosine of 2a. Now let's develop a formula for the sine, right? The sine is a little bit quicker, and so is the tangent, because there's only 1 formula for those instead of 3. And you'll see why in just a moment. So let's get rid of all this. We'll start the derivation in a very similar way though. Right? So with the sine of 2a, again, it's equivalent to the sine of a plus a, because a plus a is 2a. Then we replace the a and the b with a and a in the formula. So we would end up with the sine of a times the cosine of a plus the cosine of a times the sine of a. Everything becomes an a in this formula. Now notice that sine a cos a and cos a sine a are really the same term. It would be like taking xy and yx. They're the same term, just in a different, the factors are in a different order. And so we're really looking at 2 of them added together, 2 of the same thing. So you could think of this as 2 times the sine of a times the cosine of a, right? 2 of the same thing added together. And so this formula is equivalent or this expression is equivalent to the sine of 2a. It doesn't have a nice cosine squared or sine squared that we can use a Pythagorean identity with. So I can't really, break it down into more identities because we don't have a way to incorporate the Pythagorean identity or really any other identity at this point. So the sine of 2a has only one formula, and that is 2 times the sine of a times the cosine of a. Right? Now, the final step is a similar step with the tangent. So we're going to take the tangent of 2a and split it apart and call it the tangent of a plus a. Again, replacing both the a and the b with a and a. So everything in this formula will become an a, all the angles, and you'll end up with the tangent of a plus the tangent of a all over 1 minus the tangent of a times the tangent of b, right? With this expression, as we combine things, tangent a plus tangent a, well, that's 2 of the same thing again, so it's 2 times the tangent of a. And on the bottom, we have 1 minus, now here, oh, you know what, I missed something. Going a little too fast. This d shouldn't be a b. Hopefully you caught that on me. That should have been an a, right? Change everything to an a. So here I have tangent a times tangent a. The product of two tangent a's is tangent of a squared, or tangent squared of a. So this would be tangent squared of a, all right? So we've got 2 tangent a over 1 minus tangent squared of a. That's going to be the new expression for the tangent of 2a. Now here I do have a tangent squared. I could try to incorporate a Pythagorean identity with the secant, but I don't think that it really simplifies things. It almost makes it a little more complicated. And so we leave it at just this one formula for the tangent as well. All right, so I'll summarize that over on the side. The tangent of 2a equals 2 times the tangent of a on top over 1 minus the tangent squared of a on the bottom.